questions and problems to solve today. Um, I got a couple of actually emails regarding to um, computing aspect ratio. I'm going to talk about that first, and then have some examples and also some performance examples. We're going to cover those. But before that, so the general things that we learned um, last class or previous classes um, was that the performance actually is not just related to number of um, instructions in a code and clock cycle, but also to clock per instruction. And clock per instruction is computer architecture, how to design a hardware to can actually execute faster one instruction. That's important part that you're going to see in some example today. Um, so last class we talked about a spec ratio. Um, a spec is actually organization, a standard performance evaluation corporation. And this company making different softwares for different part of computer. Some software for memory, testing memory, we call them benchmarks. And these benchmarks are kind of centered to test some specific part of CPUs. Some part for example, ILU, some part of ILU just instruction related to integer or instruction related to floating points. So if we want to test or get the performance of one CPU, we need to do many of them and kind of make average for that. The good point about this organization is that there is a reference computer that they already did test by those references. So when you want to use, for example, one benchmark for integer numbers, they also give you some reference. They say, okay, we tested this benchmark with this computer, with this specific computer, and the runtime or execution time for this benchmark was 5 seconds, for example. And you can test that benchmark with your computer, same benchmark, and you get, for example, 10 seconds. And then you can compare your performance compared to the reference. This is going to give you an overall view. You can see, okay, in overall, my computer is better than reference or worse than reference. And this gives you an overall idea. Okay, that's a good point about benchmark. So what else we can, yes, first, we already had this slide. I'm just going to cover. One part is important to talk more. So as I mentioned, each benchmark actually focusing in one specific part of CPU. So, and we need to make overall, or we need to average them, but not normal average. We need to use geometric average, and we're going to see why. The reason of doing geometric average is that those values that you are averaging are not normal numbers. They are ratio. So for ratios, they're not like, they don't have, um, for example, they are not like time, they are not like degrees, they are not, they are ratio. And for ratio, or for not just ratio, sometimes even for actually proportion, also we are using, if you want to average proportions, you need to use geometric average instead of like mathematical average. And here also, that's the reason. So arithmetic mean or arithmetic average is just for normal things like time, score, measurements, um, and for um, values like proportion or ratio, we always use geometric average. Okay, that's the important part. And what is geometric average? Instead of adding them and divide by number of them, we are multiply them and get, like, if there are n of them that will multiply them, you need to get the root n of in overall. So that's the formula that you need to use. Okay, we already talked about that part before. So let's do that example, because I got many actually emails regarding to that. We have in this example two computers that we want to actually, and two benchmarks. You have two computers, A and B, and two benchmarks. Anytime we are talking about aspect ratio, we have reference. If we don't have aspect or reference, and still we want to compare two computers, and we have more than one benchmarks, in that case, you need to use a speed up. We're going to see in the next example. But anytime you have ratio, aspect ratio, you already given references. You have some references. References means we run this benchmark, B1, for example, and it was 100-second execution time. And we run for computer A, it was 50, and for computer B, 25, just benchmark number one. For benchmark number two, the reference is given 200 second. They are all second. They are time that is spent to run that, to execute that benchmark. For benchmark for computer A, benchmark 2 is 100, and for computer B is 80. Okay, so to find ratio, we just need to divide reference by them. Oh, okay. What happened to this? Oh, okay, good. Okay, so if you want to find ratio, I mean aspect ratio, so let I write it here. Aspect ratio is for benchmark B1 and benchmark B2 for computer A and computer B. We just need to divide reference time. For a reference, it was 100, and for computer A is 50, and for computer B is again 100 reference, and for computer B is 25, and for benchmark 2 is 200 divided by 100, and 200 divided by 25. Okay, if we write answers for this, it's going to be 2. It's going to be 2.5, 4, and 2. Okay, this actually is this table that we had last class, coming from these equations. So each of these coming from this is a spec ratio, reference time over test machine time. Okay, now that we have this, we need to make average. We need to make mean, but not normal mean. We need to make geometric mean. So geometric mean for computer A is this. Just multiply them together and get a square, because this 2 is like a square, normal square, and it's going to be 2. And GMB is 4, 2.5. It's going to be about 3.16. Okay. In this specific example, if we get, instead of geometric mean, if we get like normal arithmetic mean, still this number going to be around 3 point something. But it's not always like that. In this example was a geometric mean and arithmetic means almost showing similar result, not same numbers, but similar result, like showing that. Okay, first of all, I want to ask you, which computer is faster? No. A is faster. Why?
Has lower G, as well as the fact that both of its ratios are smaller than test machine B.
Ratio is not the number. This ratio doesn't have unit. Doesn't have unit. Remember? So if this geometric mean is higher, it means the performance is higher. It's not time. It's not time that you say, okay, it's 2 seconds, for example, so this is faster. No. Any of this that is bigger, that shows faster because they are ratio. That was my question. So the important part is that one. So because is ratio comparing ratios, so any of this that is bigger showing higher performance. So computer B is faster. Computer B is faster. That's the important part because it's ratio. So you can also check, for example, in B1, computer A is 2 times faster than reference. Because what we divided time here, reference time, to, okay. So to just clear that, for performance is 1 over time CPU. And speed up is performance A, speed up A over B. I don't know why. Okay, A over B is performance of A over performance of B. So is time CPU B over time CPU A. We need to consider this as well. A speed up of A over B is performance of A over B, but because performance and time are reversed, so it's going to be time, CPU time of B over CPU time of A. So that's why we have reference time of reference in the top, like that. So spec is kind of a speed up. So if the speed up is bigger than 1, so it means computer target that is, for example, A is faster than B. Okay, so I just wanted to clear that. We're going to have more example. Don't worry. These notations are a little tricky, but we're going to have another example to show that. Okay, before to jump to another one, do you have any question about this? We had that last class as well. I'll just repeat it. Oh, okay, so that's a clear version. Don't need that. Okay, so you do this one with iClicker. We're gonna define it. Okay, there is again 2 computer A and B, and we want to use benchmark, but in this case we don't have reference. We just computed a spec here. So okay, so I just need to run it. I want to see which computer is faster, and oh, okay, start class, pool. Okay, is it started? You can. So in this example, we have 2 benchmarks, and we just have already given spec. For spec 1 is for benchmark 1, and spec 2 is for benchmark 2. This is for benchmark 1, benchmark 2. So we get these 2 results. These 2 results for benchmark and benchmark 2 for computer A, and these 2 results for computer B. So I'm asking which comparison is correct. First, you need to see which one is faster to find. Okay, so let's see. What is your, any response? Are you able to do that? Let's see. Oh, result. Okay, I see some C. Okay. Yeah, for sure, geometric mean is correct one. So one of these 2. But which one? A is faster or B? So to do that, you need to find geometric mean of A and geometric mean of B. Geometric mean of A, because it's just 2, is a square root of 10, 40. And this is going to be a square root of 20 and 5. So it's about 420. This is going to be 110. Okay. So which one is faster? Computer A is faster, 2 times faster. So C is correct. And most of you guys did good. Good? Any question? Okay. So let's close this. Okay. Why is not clear? Okay. Any question? That wasn't bad. Okay, this is another way to look at this benchmark stuff, but this is not a spec benchmark. There's no reference here. As I mentioned, if there is no reference to compare two computers that also you have multiple benchmark, still you need to use geometric mean. But you need to find a speed up for each case and then get geometric mean. So in this case, we have two computers, A and B, and two benchmarks, no reference. So and they are execution time. So it means benchmark 1 take 10 seconds in computer A and 5 seconds in computer B. Means computer A is 2 times faster, but in benchmark 2 is not like that. In benchmark 2, actually, computer A takes 1 second and computer B takes 2 seconds. So computer A is 2 times faster because it's time here. Okay, so we find a speed up for each benchmark separately. So a speed up, okay, so the formula for a speed up, we had that before. I'm going to write it here again as a reference. Speed up, but the speed up has another things as well. What over what? A speed up, B, like for example, B over A, computer B over A is, or maybe I say A over B. Yeah, A over B is performance of A over performance of B is equal to time, CPU time, of B over time CPU A. This formula gonna give you a speed up of two computers, A over B. Here we are computing a speed up of A over, actually B over A speed of B over A. That's why we have 10 over 5. Okay, we want to see is B faster than, like B is the main computer that we want to find how faster or slower is that, okay? And again, for benchmark 2, also we want to find how is a speed up of B over A. So we put the time of A top and time of B down. So that's what base of that formula is easy. So as you can see, if we get numbers for these two, it's going to be 2.5. And when get geometric mean, it's going to be 1. So it means these two computers almost have the same performance. So on average, the two computers have equal performance across these two benchmarks. But maybe for other benchmarks is going to change it a little bit. But if we just compare them for these two specific benchmarks, they are equal. So these two computers are based off these two benchmark has the same performance. Okay, any question about that? So the main point of this example was that still we use benchmark, but not a spec benchmark. And we don't have reference. If you don't have reference, you need to make reference kind of. We use benchmark, we use actually a speed up for that. That formula helps us to see for each benchmark which one is faster, and we make average. How average? Geometric mean. Because they are actually, they are not normal numbers. There is no unit in this, okay? It's ratio. Okay, so that was good. Let's do another example. We had also performance problems last class. You're gonna have two, and one of them is actually very good question. You're gonna have one of these in your assignments, in your exams. You had in your assignment. Did you start your assignment? Have you started yet? Well, you have three questions, and um, try to solve them by yourself, please. Don't use uh, ChatGPT or AI tools. Uh, you can get help. I can check, but I want you to learn something, okay? Try to do it at least by yourself, and then if you want to get help, no problem. And we have a TA. I got a TA for you guys, so it's going to be easier for marking, and you can just write them up, but write them clean in a PDF format and send it to me. And for exams also, we can do that. We can just make it, but try to, if you write by hand, try to write it clean and readable. Okay, so let's do this example. What is this example? This is actually performance or a speed up of two computers. It's actually a simple question. You have two computers, A and B. Computer A, I write it up. Okay, computer A has a clock cycle time. Clock cycle time, the notation that we use for clock cycle time is a lowercase t, and we write cycle here. T cycle is 250 picosecond. Okay, picosecond is 10 power minus 12 second. Okay, and also clock per instruction is 2. Okay, clock per instruction. It means each instruction, so this is, for example, code and its instructions. Each instruction need 2 clock. Okay, I have a question right now. Can we have, for example, clock per instruction not integer, like, for example, 1.2? Is that correct to have, for example, clock per instruction 1.2? Is this possible? Any response, any idea? Can we have like clock per instruction not integer, like a real number?
Well, I think like
We had in one of
it
examples.
wouldn't necessarily take 1.2 clock cycles for one instruction, but like you could say that on like if there was like 12 clock cycles, 10 instructions on average would be done. Is that?
No, that's for just a specific instruction. But we always say this is average. This is average. But average of what? Average of many different type of instructions. We have different type of instructions. Some of them are faster. Some of them are slower. Some instructions need memory, for example. Those instructions need more cycles. So when we add them together and make average, so that becomes 1.2 or 1.3 or 3.2, whatever. This is average. So yes, we can have not integer clock per instructions. Why? Because some instructions are need more clocks, and we would add them together and make average, it becomes, for example, 1.2. So this is possible. So this just came to my mind, I wanted to mention. But at the same time, I wanted to tell you not all instruction in computer need same timing. Some of them need more clocks, some of them less. Okay. This 1 point. Okay, so we have this computer. We have another computer, B. This one, T cycle or clock cycle is 500 picosecond, 10 minus 12, 500 second. Okay, and which computer is faster and how much faster? To find that, we need to find a speed up. A speed up is those ratio that we always use. A speed up, but in a speed up, we need to say what over what. We say a speed up of B over A, for example, is equal to time of A over time of B. And what is the time of A over B? In this case, because we are using same program, so this number of, okay, so maybe I write the complete formula first. If the number of instructions be instruction count, IC, okay, so TCPU, it means execution time, is equal to number of instructions count, multiplied by clock per instruction, multiplied by T cycle, or clock cycle time. Or we can write clock cycle time as a frequency. So it's going to be same instruction count, clock per instruction, over clock rate, that is mostly F. Notation is F, that is clock rate. So we need to know this formula. Okay, so in this formula, we have instruction count or number of instructions in that code, sample, or benchmark, whatever, but we don't know that here. But who cares? Because if we put this here, these two gonna cancel out each other because it's equal for both of them. So that's actually we had in your quiz also the question like that, and some of you guys asked me a question about that. That's actually the point. So here we can write it up just based off this. Doesn't need to have number of instructions or instruction count. So we just can write this is 2 over 250. This one is a 1.2. What this, yeah, after, okay, so we need to multiply. I forgot to write clock per instruction for this. Clock per instruction for this one is 1.2. Okay, maybe I clean this code. Okay, so we have these two computers. Clock per instruction is 1.2. So we just multiply this together. And when we multiply, because both of them are picosecond, this 10 power minus 12 are also going to get canceled. And one it's going to be 500. 500. So the result's going to be, okay, 1 over 1.2. Okay, we should write the speed off of A over B, actually, but doesn't matter. If we write it like that, we can say, okay, I'm going to ask you, which computer is faster? We computed a speed up of B over A. So B over A is 1 over 1.2. So which computer is faster? Yes? Computer B is faster? Any other? So it means computer A is faster. Computer A is faster. Why? Because, okay, we are a speed up of computer B over A is less than 1. So this means computer A is faster. So this is showing that computer A is, okay, maybe I write the other way before that. A speed up of A over B is going to be T of B over T of A, and T of B is 600. This is going to be 500 almost, is 1.2. So a speed up of A over B is 1 over 2, means computer A is 1 over 2 times faster. Okay, I'm going to answer. So this is showing a speed up of B over A. It means computer B is 1 over 1.2 faster. So it means it's slower because it's less than 1. Good? Because it's less than 1 means same. Yeah, the point is this which over which. This is important part. Okay, so that was good example. We have another example that's gonna actually, oh, they have solution here. Let's clean this up. So same way, and so computer A is faster. How much? Like 20% faster. Why 20% faster? Because it's 1.2 low. So is that correct? If it's 1.2 times faster, is that showing 20% faster? Because that's, if it's 1, it means they are equal. It means 0.2 or 20% faster. That's how we can, yeah, but don't need to be too much details about, don't need to think about too much details. But yeah, that's actually good. Let's have this almost last one. That's a design problem. That's a very good example. You're going to see these type of examples a lot. So you have one design, and you want to make a new design that, for example, are be better or has some certain characteristic. So in this example, we have one computer A, okay? And execution time for computer A is given. So we say, okay, we have a benchmark, for example. This benchmark, we just know that the time to run for computer A is, for example, 10 seconds, T CPU, okay? And clock rate, here, clock rate given, okay? So we have that as well. The formula that coming to our mind need to be like that. T CPU is equal to instruction count, the number of instructions, clock per instruction, how many clock need each instruction, and time is, this is lowercase, t cycle. These notations is good to follow them. Is exactly if you want to use frequency, we need to bring frequency down because time is a reverse of frequency, or frequency is reverse of time. Instruction count, clock per instruction. So this is the formula that we need to use for solving this problem. Okay, just remind that. First step, okay, what we want to do. We say, okay, we have a computer A, the execution time given, the clock rate given, but we want to design a new computer that is B. That we want this computer can execute this in 6 seconds instead of 10 seconds. And clock rate, and this computer has 1.2 times more clock rate than A. Okay, so that's something that we need to see what that means. Okay, so to explain what that means, first we want to see what clock cycle means. Clock cycle is okay, if you back to main formula, I just wrote them, I should here. So it's clock cycles for one program, or C, is equal to, or total clock cycle sometimes, is instruction count multiplied by clock per instruction. This showing how many clock cycle is to run that. How many clock cycle you need to run this is clock cycle. Instruction count multiply clock per instruction. This means clock cycle. We want this clock cycle be 1 point time of computer A. Okay, so that's something that we can use. Okay, so so this means this part, isn't it? So this part is given. Okay, but we don't know clock cycle for computer A. First, we need to find clock cycle for computer A. Clock cycle for computer A is given to frequency for A, time for A, based off this formula. Because this is C for computer A, is multiplying T and F. Okay, so we can write that. So if we put them together, frequency is 2 gigahertz to 10 power 9 hertz. And TA is 10, so it's going to be 20 multiply 10 power 9. Okay, so we have that. So C of B, because it's 1.2 times of that, we can find this as well. Okay, so we just need to write this going to be 24, 10 power 9. It's going to be 24 gigahertz. Okay, we don't care about that. So we find C of B. So we just need to find frequency. Ask us what is the clock rate or f of B, because we have this part and we have this part. We can find f. So I'm going to change the color to make it more interesting. F of B, oh, f of B. Oh, why it's not writing this corner. F of B is equal to C of B, that is given, T of B, that's also given here. So we have 24, 10 power 9, and T of B is 6 seconds. So it's going to be 4, 10 power 9 hertz. That's the final answer. Separated. Okay, so they are all around this formula. If you know this formula, you can find, we can change this question in so many ways. You can solve that. Okay, this kind of question is like complex one that I can ask. Okay, so we don't have time. I'm just gonna check the last one. Any question about it before jumping to the next? Okay, but if you have question, you can always send me email. This one is about power. Power doesn't have that much issues. So we know the power is a ratio of capacitance of transistors, voltage, and frequency of switching those transistors. So we have for two computers, new and old, this change. So new capacitance is less, voltage is less, frequency is less. So for sure, the new gonna have less voltage. If we do, it's like a speed up here, but for voltage. If we do that, we can see the new computer has like 50% less need less voltage. Less power. Sorry, less power. Okay, so that's it. Any question? More questions? Have a good day. See you Friday.
I didn't catch the like access code for the attendance thing.
Wait a second.
I didn't want to like.
Sorry, wait a second. I just turn off this video to not recording.